Large language models are incredibly powerful, but they have a critical weakness. They can confidently invent facts, a phenomenon we call hallucination. To ground these models in reality, we use a technique called Retrieval-Augmented Generation, or RAG. But what if the retrieval step itself isn't perfect? What if the best information gets lost in the noise? That's where our story begins. At its core, RAG is a two-step process. First, when a user asks a question, we don't send it directly to the LLM. Instead, we use the query to retrieve relevant documents from a knowledge base like a set of PDFs, a database, or a website. Second, we take these retrieved documents, bundle them with the original query, and feed this augmented prompt to the LLM. The model now has the specific context it needs to generate a factual, grounded answer. The retrieval magic happens using vector embeddings. We take our documents, split them into manageable chunks, and use a special model called an encoder to convert each chunk into a list of numbers of vector. These vectors capture the semantic meaning of the text. When a query comes in, we encode it into a vector too. Then, we perform a similarity search, like a cosine similarity, to find the document vectors that are closest to our query vector in this high-dimensional space. These are our top candidates. This initial retrieval, often called naive or first-pass retrieval, is incredibly fast and powerful. But it's not perfect. It's optimized for speed, not precision. The retriever might pull in documents that are only tangentially related or contain just a keyword match. Research has also shown a lost in the middle problem, where LLMs pay more attention to context at the beginning and end of a prompt, potentially ignoring the most relevant document if it's buried in the middle of a long list. This is where a Reranker model comes in. A Reranker is a specialized, smaller model that takes the initial, broad list of documents from the retriever and resorts them based on a much more precise calculation of relevance to the original query. Its only job is to take a list of, say, 25 documents and give us the absolute best 3 or 5. It acts as a quality filter, ensuring the final context passed to the LLM is as potent and relevant as possible. So how does it work? Unlike the initial retriever, which encodes the query and documents separately, a common type of Reranker called a cross-encoder looks at the query and each document together. It concatenates the query and a document, passes them through a sophisticated transformer model, and outputs a single score indicating their relevance. This joint processing allows the model to deeply analyze the interactions and nuances between the words in the query and the document, leading to a much more accurate relevance score. Let's clarify the distinction. The initial retriever typically uses a biencoder. It creates separate, independent vectors for the query and documents. The comparison is a simple, fast dot product. A cross-encoder used for re-ranking is different. It takes the query and a document as a single input pair. This allows for full self-attention across both texts, capturing much richer interactions. The trade-off is speed. A cross-encoder is much slower because it must rerun for every single query document pair, making it unsuitable for searching over millions of documents, but perfect for re-ranking a few dozen. So let's look at our upgraded RAG pipeline. The user query still goes to the retriever first. But now, instead of retrieving just a few documents, the retriever fetches a larger set, say the top 25. This entire set is then passed to the Reranker model. The Reranker does its computationally intensive but highly accurate scoring and returns a new, reordered list. We then take just the top 3 or 5 from this new list to build our final prompt for the LLM. How do we know this extra step is worth it? We use evaluation metrics. A common one is hit rate, which measures whether any relevant document appeared in our final top K list. Even better is mean reciprocal rank, or MRR. For each query, you find the rank of the first correct document. The reciprocal rank is simply 1 divided by that rank. MRR is the average of these reciprocal ranks over all your queries. A higher MRR means your most relevant document is consistently appearing closer to the top of the list, which is exactly what a Reranker helps you achieve. While powerful, adding a Reranker isn't always a free lunch. The primary trade-off is latency versus accuracy. A reranker adds an extra computational step, which increases the total time to get an answer. You need to decide if the boost in quality is worth the slight delay for your application. You also have choices for models. There are large, powerful rerankers and smaller, faster ones. You must balance performance needs, infrastructure costs, and the desired level of accuracy for your specific use case. Implementing a reranker is often simpler than it sounds, thanks to modern libraries. You'll typically instantiate a reranker model from a library like Hugging Face Transformers or a dedicated provider. You retrieve your initial documents. Then you create pairs of the query and each document text. You pass this list of pairs to the reranker's predict or rank method, which returns a list of scores. You can then sort your documents by these new scores to get your final, relevant sorted list. In summary, retrieval-augmented generation is a fundamental technique for building reliable AI systems. While the initial retrieval step casts a wide net to ensure we don't miss potential information prioritizing, recall, reranker acts as a precision filter. It meticulously re-examines the top candidates to ensure that the context we provide to the large language model is the most relevant and potent. By adding a reranker, you can significantly reduce noise, mitigate the lost in the middle problem, and ultimately build more accurate and trustworthy AI applications.